exam from last year and updated study guide. If you're a W student, you have a formal paper due this Friday, and I haven't had any questions about those, so I'm assuming you're doing okay. If you're not, you're probably going to come see me. Yeah, no, you already talked about it. It's just, don't store it in the fridge for a year, or even worse, at room temperature, because I don't want the bottles to split. We are starting chapter 16 today, which is glycogen metabolism and gluconeogenesis.
Maybe I have to actually take notes. I thought this was a brunch party.
Metabolism. So glycogen was mentioned back in chapter 8, carbohydrates, and what is its function? Glucose storage for energy. It is a polymer of what? Yep, D-glucose. And what kinds of linkages? And
Alpha 1,6.
so it's branched. Every time there's an alpha 1,6, there's a branching point on the main chain. Glucose gets mobilized from reducing or non-reducing ends.
Non-reducing.
Why?
There's more of them.
More of them. There's more of these. One reducing end. And that way it can be more rapid if you are desperate for some glucose. And then metabolism requires 3 enzymes. So we're going to go through each of those. Glycogen phosphorylase. And this catalyzes phosphorylases. I guess we'll have a mixture over here. No, it's just a lot. Extract. This is, it kind of means hydrolysis with phosphate. Instead of water. This is where the name comes from. So if you're doing a hydrolysis, you're breaking bonds with water. If you're doing a phosphorylasis, you're breaking bonds with phosphate. In this case, we have glycogen that is N-glucoses long. And you add a phosphate to that. And this is an equilibrium process. Glycogen, 1 glucose less than it was, plus the glucose 1 phosphate. And the second enzyme is a glycogen debranching enzyme. We're just going to get rid of our alpha 1,6 linkages for us. And the third enzyme you need is a phosphogluconeogenesis. And this is going to convert glucose 1 phosphate into wet, I can go into glycolysis.
G6P.
Yeah. Into a 6-phosphate. So it can enter glycolysis. Okay. So just a reminder of what glycogen looks like. Somewhere there is a main chain that has a reducing end. Somewhere. But that will be the only reducing end. And every other end is going to be a non-reducing end. And then we have these branches. These are all alpha 1,4 linkages, but every once in a while you have an alpha 1,6 linkage. You're going to see that those have to be at least 4 residues apart for a branch. And so then this is the cartoon version of what glycogen looks like. It's just this nasty, bloody polymer. But all those non-reducing ends make it fairly quick to break glycogen down if we need it for energy. And our first enzyme, glycogen phosphorylase, it's going to use acid-base catalysis, and it's got a funny cofactor here. This is one that you haven't seen before. So pyridoxal 5'-phosphate, also known as PLP. I'm not worried about knowing the structures of these. But what it provides is this kind of convenient phosphate group in the enzyme that is going to take part in the acid-base glycolysis. Okay. So we have our PLP, so PL, and then this is the P for my cofactor. And then the blue just represents the enzyme. And then I have glycogen and a phosphate that come in. And we're going to have a kind of series of proton exchanges here. So the PLP gives up a proton to the other phosphate. It then gives up a proton to break the glycosidic bond, the alpha 1,4 glycosidic bond. So basically this oxygen gets protonated and that promotes bond cleavage. I end up with an oxonium ion intermediate. And then the phosphate will act as a nucleophile and come in and add at that one position. And again, there's some shuffling of protons here to get that to happen via that PLP. So that's a big element. We've seen this before. What enzyme uses a similar mechanism that we've already studied? No one picked none of these? What it was?
Was it?
Okay. Let's try it this way. Of these 3 enzymes that break different things down, if you can think about what sort of substrates they work on, which of those substrates most resembles glycogen? Which of those is a polysaccharide acting enzyme? Let's see if we got it here.
Oh.
Now it's none of these. Yeah, here's lysozyme. Use lysozyme. Those of you in lab, you're going to have to eventually write a report about lysozyme by the end of the term. And for the first one, you don't have to worry about mechanism, but for the second one, you need to worry about mechanism. So that's something you might want to go back and review. But it was very similar. The very first step in breaking down that peptidoglycan was a protonation of the glycosidic bond, where then this whole group just leaves, and you're left with that oxonium ion intermediate. The difference is what is acting as your acid and your base in this case. So we have this PLP chromosome cofactor for this enzyme, but with lysozyme, it was just amino acid side chains that did that. glycogen, phosphorylase, things you should be able to know. This requires PLP coenzyme, which stands for pyridoxal 5' phosphate. And that's a B vitamin derivative, if you care to know that. It uses acid-base catalysis. Via the PLP. It involves a half-chair oxonium ion intermediate. And last thing you should know about this enzyme, that is unable to break glycosidic bonds. And that's alpha 1,4s that we're doing right now. Closer than 5 residues to a branch. Yeah, I would imagine that's what fits into the active site, and at branching point, there's this great big group coming off, and at some point the enzyme can't get in to where it needs to work. Okay, glycogen debranching enzyme. This transfers remaining alpha 1,4 linked sugars in the branch to a non-reducing end. And another branch for the main chain. It leaves one residue attached. Via the alpha 1,6 linkage. Which is hydrolyzed by a second active site on this enzyme. Glycogen debranching enzyme is a bifunctional enzyme. It acts as a transferase and it also acts as a hydrolase. And we'll see that in more and more examples where we've got these enzymes that have more than one domain to them and more than one active site to them. There's 2 active sites. One hydrolase and one transferase. Okay, so here's the branch, and then they're treating this as your main chain or another branch. But initially you've got the phosphorylase comes along, it's chopping off all those glucoses, and then it gets into the branching. Right. And it could be going along this one and then get stuck. It could be going along this one and get stuck. As soon as you let the transporters goes away and on the big one is the branching residue. Those four can be transferred to another non-reducing end. So all four of those, I guess three of those would get moved, and then the fourth one here gets left behind, and that's the one that's just hydrolyzed. And that one's not a mechanism we're going to do. Next. So phosphogluconeutase. Transfers, G1P, G160 to a G6P. So it has a bisphosphate intermediate. Convert your 1-phosphate to a 6-phosphate. And this is going to use a phosphorylated serine. In the active site to mediate kind of two phosphoryl transfers. But it's all intramolecular, so this is an isomerase.
Does phosphorylate mean anything?
Does what?
The
Did I write phos twice?
I was curious if I missed it.
No. That is me having a second thought and then restarting the same way.
I didn't even notice.
I just wrote phosphorus.
I thought it was a new word.
It has a phosphos.
Yeah.
Instead of bisphos,
So
Phosphos.
it's like things like that, and then on the exam that shows that it's diphosphorylated, and I'm like, where in the world did that come from?
Phosphos.
Okay, so here's my enzyme, here's my serine, there's a side chain, it's phosphorylated, and I transfer that phosphate group to the G1P. We make a bisphosphate on 1N6, or on 1, yeah, and then transfer it to the number 6 position, make our 1,6. And then I transfer the one that was on the number 1 position back to the serine to regenerate the active site, and that should look really familiar. So which enzyme does that look like?
No. Is it AB?
Yeah.
Yeah, the code statement. Okay. Okay, so wow.
Take it C wasn't the right answer.
So what other bisphosphate? Well, it wasn't really a bit. It was a single phosphated group that has a bisphosphate intermediate that looked like something else that we'd seen before, but that ends up being a monophosphate again at the end.
What's wrong with steps?
Do you have to think about where in glycolysis these pathways, these enzymes are? phosphoglucose but it's not. It's phospho what? Glycerate. Yes, phosphoglycerate mutase. And so I purposely did not write a PGM when I wrote this new enzyme, the phosphoglucomutase, because if you say PGM, I'm referring to this one, I'm going to assume you're referring to the glycerate mutase instead. So PGM is usually used for the glycolysis pathway enzyme and not this enzyme. So this enzyme you should write out. So that was when you had your 3-phosphoglycerate and you had to convert it to a 2-phosphoglycerate, and it was done via a 2,3-bis phosphate intermediate. And what was your phosphorylated side chain? It wasn't serine. It was histidine.
Histidine, yeah.
Same idea, exact same mechanism. Yeah, you have to have it all memorized, but.
Little weak.
So this is similar to PGM, which is the phosphoglycerate mutase. Okay, so our outcome, glycogen metabolism. You generate glucose 6-phosphate, which can enter glycolysis at what step? So in glycolysis, the first thing I do is make a glucose what? 6-phosphate, and so step 2, right, you're going to enter at step 2, where you're going to convert it to the fructose. It's already phosphorylated. So it skips the first energy consumption step. Does that mean that it's more energy efficient to get your glucose from glycogen than it is to get it straight from glucose? Not really, why not? You have to turn into glycogen first, which we're going to do next. Okay, so we're going to turn into glycogen, and that's going to cost ATP to do it. So, so this is a but. It consumes ATP to make glycogen. So your end energy is the same, regardless of the source. So anything that you eat, we eat starch all the time, is always broken down to simple sugars to go through the bloodstream. And then in your liver, you're going to convert it, and some in muscle as well, but you're going to convert it to glycogen to store it. And it costs ATP to do that. So then when you have to use your glycogen stores to get glucose back out, you skip that first step, but you've already consumed the ATP initially stored as glycogen.
Is there a way to inject somebody with glycogen?
I hope not, because it's this icky insoluble polymer. You usually don't want to inject people with insoluble stuff.
Usually.
There's no way to get out of the bloodstream.
Is heroin soluble?
Yeah.
Yeah.
The melt it. So it's like a liquid.
Still, all the liquids are soluble in water.
Okay, very much.
I think so.
Alright, so
If they mix
net
it with
cost
water
is the
when they
same.
heat it up, and that's when they heat it on the spring, right?
Yeah, but then you just take a syringe and go like that and inject it. There's no water and stuff.
Okay, so glycogen
I thought you heated
synthesis.
it up with water.
Just spoon and torch.
So, heroin.
Breakdown has a delta G of about -5 to -8 kilojoules per mole. So So that is going to be a spontaneous process to break down glycogen. So glycogen synthesis has to happen by a different pathway. It can't be backwards for glycogen catabolism because the energy says we can't go that way. So our synthesis is in 3 steps. We need a UDP glucose pyrophosphorylase. We need glycogen synthase. That's going to be really important as a control point. We'll see that later on. And we need a glycogen branching enzyme. And I should put in parentheses here, synthesis is in 3 new steps. Because actually the first step is identical to the catabolism. So this figure kind of shows our cyclic process here for getting glucose out of glycogen, putting glucose back into glycogen. We already saw the debranching enzyme and the phosphorylase to get to glucose 1-phosphate, which can be converted to glucose 6-phosphate. To go back the other way, it is specifically these steps that occur through an alternate pathway. So this first one, the glucomutase, is pretty much at equilibrium. It's going to go back and forth between the two. So 6-phosphate is converted back to 1-phosphate. But then I need this UDP glucose pyrophosphorylase, and then I need glycogen synthase, and I need the branching enzyme, and then there's kind of this side reaction that isn't actually part of the synthesis, but is needed to couple, to energy couple the first reaction into something that is actually energy favorable. So we're going to write this out. So for that first one, UDP glucose pyrophosphorylase. And so we're starting with a glucose 1-phosphate. And we're going to consume some UTP. And that gives me UDP glucose plus pyrophosphate. And the standard free energy change on that is approximately 0. That is an equilibrium process. But if we want to synthesize glycogen, we're going to figure out a way to pull it forward. And so that's actually done by hydrolysis of the pyrophosphate. And there is an enzyme for that called inorganic pyrophosphatase. And that free energy change is a negative 19.2 kilojoules per mole. So our first reaction is coupled to the exergonic hydrolysis of pyrophosphate. analysis is proximity orientation. Similar to the kinases you've seen, because the kinases are also proximity orientation to do phosphoryl transfers. And here, we're not transferring a phosphate group or phosphoryl group, we're transferring a UMP. So this is my glucose 1-phosphate. It's my nucleophile. It attacks the alpha phosphorus of UTP. UTP is just like ATP, except that it's uridine instead of adenine, is all. So it attacks that alpha, and then my leaving group is the pyrophosphate. And this is shown as concerted. It probably isn't. There's any phosphosyl nucleophilic attack is going to involve a pentacovalent intermediate. So again, that's kind of lazy biochemistry line right there. Okay, so then I end up with my UDP, where 1-phosphate came from my glucose 1-phosphate, and the other phosphate came from UTP. And then pyrophosphate, again, is helping pull this forward by being hydrolyzed to release lots of energy. So then, our second one is glycogen synthase. And that's going to take UDP glucose plus glycogen of N units long. And we're going to release our UDP plus glycogen as now N+1 units long. And that standard free energy change is equal to negative 13. Negative 13.4 kilograms per mole. So by making this kind of high energy intermediate, this UDP glucose, that makes the transfer of the glucose to the end of your molecule easier because we're going to break down the high energy compound. So UDPG is added to a non-reducing N. And this is going to form an alpha 1,4 linkage. And the mechanism is similar to our lysozyme and similar to our glycogen phosphorylase. In that it uses an oxonium ion intermediate. Okay, but this is not a mechanism your book works through, and I'm going to make the assumption that it's not completely worked out as to what is acting as your acid and base group for this enzyme. Okay. Last thing you should know about this particular step is that consumption of UTP is equivalent to consumption of ATP because UTP is regenerated and this way. So UDP plus ATP goes to UTP plus ADP. That is how you make your UTP for the next round. You actually consume ATP to do it. So we're going to talk a lot about ATP equivalents, and we're going to use GTPs and UTPs and DTPs and CTPs, whatever I've forgotten there, as equivalent to ATP, because in order, if you hydrolyze one of those, in order to turn it back into the triphosphate, it's always via transfer from ATP. And one more thing for this one. This can only extends glycogen chains. It requires a completely different enzyme that we're not going to talk about to start a new one. Glycogen branching enzyme. And this one is I'm going to transfer the residues to a branching point. So this transfers 7 residues to a C6 hydroxyl to start a new branch. And the 7 residues must come from a branch that's at least 11 long. Okay, if it's coming from a branch, then it's a non-reducing end, right? And then the branches must be greater than or equal to 4 residues apart. And this is also a transferase. Oh, sorry, this is the last one. So that was my UDP glucose, where I lose the UDP, and it ends up just leaving. And again, we don't know what the acid group would be to protonate it to get to the, but then you end up with oxonium minor intermediate, and then the end of your glycogen chain just acts as the profile after that. Okay, but then for our branching enzyme, if I get something that's at least 11 long, then I can take the last 7 residues of that branch and I can transfer it to a new C6 position to make a new branch. But this branch has to be at least 4 residues away from the last branch so they can get closer together than that. Yeah, sorry. Contemplating whether we should move on, so I'm going to 10 more minutes. A lot of stuff to cover. Go for it?
Yeah.
Okay. The next Friday, let's take I don't have any slides though, so
There's so good stuff for that.
doesn't look good anymore.
Okay, there's one. So this is
Okay. Control of glycogen metabolism. We're going to see examples of allosteric control. So again, that's some inhibitor or activator that binds to an enzyme in our pathway at some site other than the active site. We're going to see covalent modification. What's our favorite covalent modification? Phosphorylation. Yeah, we're going to see some of that in control of glycogen metabolism. And these are all related to each other, but we're going to see all of this kind of under hormonal control. Okay, so if we do allosteric control, we're going to see that with glycogen phosphorylase. Okay, which does what? Which pathway is this one involved with? Glycogen breakdown or glycogen synthesis? Breakdown. It's got inhibitors and activators.
Let's see.
Okay. If I want to break down glycogen, it's probably because I need glucose. Although some things work counterintuitively sometimes. If I don't need glucose and I don't need ATP, then what do you think would work as a good inhibitor? Okay. If I don't need ATP because I have a lot of it around, then I can use it as an inhibitor for this enzyme. Because the only reason I want to break down glycogen is because I need more ATP. I need glucose. So ATP works as an inhibitor. And the other one that is a pretty good signal allosteric inhibitor for this one is glucose 6-phosphate. If glucose levels are high or glucose 6-phosphate levels are high, and again, this was the first step of glycolysis. And actually, when we actually start looking at transport of glucose, frequently you see it actually already in the glucose 6-phosphate state. And for example, you saw that fructose, when it enters the liver, is already at a glucose 6-phosphate state. Okay, so these are things that if we have a lot of them, we don't need any more of them. And so you're going to inhibit glycogen breakdown. So the activator, then, you would think it was ADP, but it's not. The cellular signal for low ATP is actually the monophosphate. Okay, so glycogen phosphorylase is under allosteric control. So is glycogen synthase. And so that name is a little more obvious. This builds up glycogen. And it also has both inhibitors and activators. If I am desperate for ATP, then I don't want to be using my glucose to synthesize glycogen. I want to be breaking down my glucose for energy. So knowing that, what sorts of things do you think might inhibit?
AMP.
EMP would be the thing you'd think of. It's actually
ATP.
Whatever.
Yeah.
Stupid.
And the other thing that goes with that, inorganic phosphate.
separate than last time.
A comma,
So
Do they have to be
ADP
together?
and- yeah,
Yes.
they need
No,
both
no,
of
no, no,
them?
or.
is it- okay.
or and. Well, no, put more. They're both allosteric inhibitors of the enzyme. I don't think you need both of them, so I don't think so. But I'm gonna put there that these are weak. And mostly controlled through activation. So it's more the presence or absence of activators than it is through presence of inhibitors. Okay. What would I have a whole lot of that might tell me I need to synthesize some glycogen? So I don't need the glucose, so I'm going to store it for later.
ATP.
You might think ATP, yes, but it's not. but that's good thinking. That's critical thinking. What else?
I hate this.
Glucose 6-phosphate. That's the big one.
Good, but no. Close. But no credit.
So that's the allosteric control. Allosteric control is easy. We're going to do covalent modification next. That is not easy. That is a whole phosphorylation kinase cascade map with opposing phosphatases, and so that we're definitely going to wait